Hi everyone. So this one is supposed to be the majority of the work actually done by one of my friends, Long, but he not be able to make it today. So this one is the agenda for today's talk. So why is the talk on this one? The thing is that most of the modern operating system nowadays have a lot of different protection for security vulnerability. So you can see there is like non-executable with NX, address space layout randomization. They have the ASCII armor address mapping, stack protector or whatever of compilation protection. And all of these protection make some kind of like exploitation harder, and especially for the technique like return-oriented programming with the really good arrest space randomization, then actually it will be pretty hard to do that. So in this talk, actually we are propose and talking about one of the practical and reliable way to, with combination of multiple different techniques, to be able to bypass NX, stack memory mapping, serial ASLR, ASCII armor protection on x86 operating system. Basically, we are demonstration is based on Linux, but we have the working stuff for BSD, Linux, Mac OS, and the upcoming one is also Windows. Basically, we use the multi-state ROP combination techniques to be able to have some of the state 0 to bypass the protection, and state 1 to do whatever you want to do. And in order to automate all of these kind of things and make it very easy to people to use, and we have the tool where we can have the practical ROP gadget catalog and also support the automation and many others, like very easy to do the stripping. And this talk is not talking about the ROP. So actually we only use ROP for bypass some of the protection. This one is not really talking about the return-oriented programming. I also not going to talk about like ASLR implementation flow or whatever information leak, compilation protection like stack protector and things like that, or mandatory access control. So I'm not going to talk about this kind of thing. So this one I will try to go very fast because it's just basic things and just a recap. This one is just the basic buffer overflow problem, and this kind of thing I think is simple things. So nowadays, like for example, the Linux, they have a lot of different mitigation techniques. Like I mentioned before, non-executable, like you have the PAS or SSL whatsoever, with the support from the hardware itself, by the CPU with NX or SD bit, or by software emulation. There is the arrest space layout randomization, like ASLR, where it supports the randomized mapping of the stack, heap, memory mapping, share library, and also the application bay, which is require the compiler support with the /PIE things. And like SSL from Red Hat, they also introduced the ASCII armor mapping, where all the share library actually will be relocated in the ASCII armor area, which is the first 16 megabyte, and which means the library address start with the null byte. So actually can stop, like having the null byte in the return. So it will be block kind of like return to libc kind of attack. And also there is the compilation protection, like the stack protector, SSP, Propoline, Fortify source, different kind of things, where they put like stack canary and stack cookie. So for example, this one is an example of how the memory mapping. You can see here the address of the library is starting with nullby, which is the ASCII ARM things. This one is not executable in this space, which is NX. And here is no PIE, so that's why the binary itself is mapping into, it's not randomized for the binary itself. And ASLR is for the stack, for the heap, and things like that. So every time you run, actually, it will load in different address. So this one is just a quick overview of like, this one is the result of the PAX test on the Fedora 13 and the Gen 2 hardened with the hardened kernel 2.632. So you see on the randomization, this one, the first one is for the Red Hat, and the second one for the Gen 2 with the PX and GR security patch. So you can see for this kind of thing, actually for like about like 13, 16 bit is actually pretty easy to prove for. And there is even some implementation flow on the previous kernel where actually you can try like about like 40, 50 times. Actually, there's some address will be repeated. So bypassing this randomized address space actually it's very dependent, right? It depends on how the ASLR implementation, the environment factor, and how the vulnerability as well. So this one is also the recap on the basic Stack Overflow and code injection. I just skip this. Return to libc, which is a simple thing where you return back to the library function. Let's say, for example, return back to the system. And like mentioned before, it will be pretty hard with the ASLR and ASCII ARM because it's actually the libc function itself is randomized, and the stack also random, so it's not easy to the location of the argument on the stack, and you have the problem with the nullby, and also it's pretty hard, and also because of nullby, it's hard to make the chain return to libc code. ROP is recently, in the last 2 years, actually it's a new term coming up. So, but actually it's based on the return to libc and borrow code chunk kind of idea, which is basically it's like the term of the gadget is like the sequence of the instruction ending with the return, but it's not necessary to be ending with return. I mean, can be ending with like jump register or something like that. So here is some example of the gadgets, like for example, load a value to register, which is pop something register and return. So you can actually load the value into the EBX register. Or for example, this one you can lib like 8 bytes from the stack pointer, or you add some value into the memory location, for example. So this things is called gadget in terms of the ROP. So with the ROP, we are always saying that with the enough number of gadgets, actually we can do the Turing complete like arbitrary computation. However, in the practical, the problem is that actually there is very limited number of gadgets where you can really use from the vulnerable binary, and the library had more gadgets, but however the randomized whatever library mapping or the ASCII ARM actually make it very difficult to do like chain or whatever ROP payload and things like that. This one is just some summary on this, where in fact this kind of thing actually very dependent on like how the binary, how the vulnerability, and the thing like that. And with the full protection like PIE, stack canary, ASCII ARM, or things like that, there is generally is pretty hard to exploit the binary with like enable full kind of protection. However, it's still dependent like in some case, for example, like remotely, you may be able, like using some fog or whatever, you may be able to brute force it. And there's some way to brute force it much faster. Like let's say you don't try one by one, but you try for every byte, and like you don't need to like try a lot of time in order to figure out what is the right value for the, let's say, the stack cookie, the base address of the binary and thing. Then you can do the normal exploitation once you figure out the address. So now I will move into the next one, which is the combination techniques, where we're trying to implement it to bypass some of those protection. The basic idea is to build a generic state zero payload where it can help to bypass, like, you know, stack memory mapping, randomize, then NX and ASCII armor protection, with the idea of using a very like minimum number of the ROP gadgets inside the binary. The reason, like I mentioned before, ROP in generic is nice to have. However, the number of real ROP gadgets inside the executable file is limited, and it's very dependent on binary and binary. So the idea here is just use only a few, which is available on most of the binary. For example, most of the binary compiled in which GCC will have enough number of gadgets to build the state zero. And from the state zero, it will be able to load the full and the complex stack, the state one payload, which is you can put anything inside the state one. So the state one payload could be anything, could be the fully ROP cell code, could be the chain libc code, or maybe just a normal cell code. So that is the basic idea of the tool, of the methodology. So the first thing for the state zero, so the idea of this one is the first thing actually we are trying to propose a way to build. The first thing we're trying to build a stack, a new stack at the node location. So with this way, actually, you can be able to full control of the stack. You don't need to worry about whatever randomized stack address any longer once you switch to the new stack. And it's easy to control the function argument and whatsoever argument on the new stack for the chain return to libc or ROP cell code. And also, you can control the stack frame. So here is an example of like the benefit of having a stack in the fixed location. For example, we choose this address, which is in the data session or some, in the data session, to use at a new location for the new stack. And from this one, you can see you can control the next text frame and things like that. And you actually can control the whole things easier. So the location for that is just any reliable location, which is, let's say, the data section or something like that. For example, in the binary, you can use like this section, like data, BSS, that kind of thing actually can use for the stack location of the stack. And actually, the state zero is the purpose of the state zero is actually to transfer the real payload of the state one into the new stack. So in order to transfer the state one payload, we can use some of the ROP, like the load. Basically, the way we're trying to implement is using just a minimum number of ROP gadgets. So basically, we only need to have something like load register, store memory to address to register, and that one is just almost enough to do the things. And so the question is, where is the data of the state one payload? So the payload itself, the state one payload itself is like, let's say I have like the state one payload is 100 bytes. So how can I transfer that 100 bytes to the new stack? So the idea is that we actually reduce on the data inside the binary itself. So the algorithm is like we can use the string copy or string f or whatever things, and we return to those functions and trying to copy the data we want from the binary itself into the new stack. So this one is the how the algorithm works. So the input for the state 0 is the state 1 payload, and the output is the state 0 payload, which help to transfer the state 1 payload into the custom stack. Then after you transfer the complete state 1 payload, then it will just switch the stack frame. How it can do that? So I mentioned before, let's say the state 1 is 100 bytes, so I just looking for the first byte, second byte, the sequence of the byte in the state 1 payload, and I searching for those bytes in the binary itself. So once I find the data, the similar data in the binary, then I will generate the string copy code where with the source is the address of the byte file in the binary and the destination is custom stack. So and keep repeating until finish the state 1. So after the state 0 done right, actually you will have a new custom stack with the full state 1 payload over there. So for example, here is an example of state 1 to transfer /bin/cell into this address. So assuming that this one is the some location in the data which is reliable, and where I want to build the new stack. So here is the PLT of the string copy, and I have some gadget to do the load to register, like load the value into EBS, EBP, and EBP you can just keep it and return. So for example, something like this. So what I can do is I can find the value in the binary itself. So I know that the value 2F is in this address. So I can generate the payload for the state 0 is something like the address of the destination, then destination source, and the next stack frame. The B3 is actually the pop-up red, which is the gadget for the load register. And this one is the PLT entry of the string copy. So I keep generating this one until it's finished. So on the state 0, on the state 1 payload already like a copy into the new stack. So at the end of the state 0, actually we need to switch the control to the new stack we just copied on the data of the state 1. So we transfer the control to the custom stack and let the state 1 start running. So we only need to have either pop EBP return and leave or something like that to switch the stack, which is available in most of the binary. So the state 0, the advantage is that actually you can, in the next step, you will have the full control of the stack, and you don't need to care about the SKMR or whatsoever any longer, because the state 1 can consist of any byte, including the null byte, in the new custom stack itself. And it's very practical. In most of the binary, we have survey like most of the distribution, like Linux distribution, and we survey all of the binary. And actually, the thing we need is available in all of the binary we check. Basically, we only need 3 ROP gadgets for the state 0, which is some load register, some S or sub memory, and one of the stack pointer manipulation, where it's something like pop EBP and leave or something like that. And for the state 1 strategy, so the state 1 could be anything, like I mentioned before. The state 1 could be the change return to libc code. Now it's become very easy, where you can transfer all the data and the location of the stack and everything. So it's very easy to do the change return to libc. or you can return back to mprotect to actually make the memory become executable again, then transfer the control to the new place with the normal cell code. And this way also work on most of the distribution, as said, like PAS, GRSec patch, security patch. Actually, if you enable like mprotect restriction, and this won't work. Or maybe you can put a fully ROP cell code there, which is simple as well. After because the state 1, there's no limitation. You don't need to care about the randomized array space. You don't need to care about ASCII armor. You don't need to care about NX anything. So in the state 1, you can do anything you want. So basically, this one is the recap on how you do the return to the PLT. So in the binary, you have the PLT and the GOT, then the real address in the libc, thing like this. So you can actually return to the PLT instead of you like return directly to the address of the function in the libc. So the problem here now is like how you can resolve the runtime library address. So the thing is that sometimes the libc function there is not available in the binary itself. Let's say I want to know the address of the string copy in the libc, and since the address is randomized, you don't know the base address of the library, and in the binary itself there's no string copy used in the binary itself, so there's no PLT entry or anything for that. So in this one, you will need to resolve the libc run address in the runtime. So let's say if I want to know the address of system, and in the binary itself there is some libc function, let's say printf was used. So what I can do is I can resolve it in the runtime by actually calculating it. Let's say from the library, when it's running, it load into the memory, right? The base address can be random. However, the offset between two functions is still the same. So what I can do is actually, if I want to know the address of the system, what I can do is like I can calculate what is the offset between the printf and system, and from this one I can just add the offset into the printf, and I have the address of the system. For this reason, we actually can resolve and calculate any address of the function in the libc, and there is gadgets available in all of the binary. So we for this one, we have a couple of different techniques for this, like GOT overwriting or dereferencing. So for the GOT overwriting, this one is like one of the favorite method for the format string, where you override the GOT entry of some libc function to some other value to code the other code you want. So the step for this one is basically we load the offset into the register and add that value which is loaded into the register to that memory location which is the GOT entry. Let's say you want to resolve the address of the system in the libc. So what you can do is you calculate the offset between system and printf, then you load it into the register, then add that value into the GOT entry of printf. So now the GOT entry of printf actually point to the system in the main. So we don't know the base address of the libc, but however we know that now is the GOT entry of that printf. It now contains the value of it point to the system in the libc. Then at the end, after we do that, we can just return to the PLT entry. And the ROP gadget for that is basically you only need two, which is one is load register and the other one is add or sub memory, which is this one, and this one is enough. So for example, here is an example that you want to resolve, you want to have, want to know the address of the exact VE. So you can call so you can exact something else. But the binary itself, in the God table itself, there's no exact VE. So now you need to resolve the address of the exact VE in order to call it. And what in this one, basically, is just override the printf God entry and make it become the address of exact VE. So basically, here's an example of the payload. This is the address of the printf in the PLT, and this one is the address of the printf in the God table. And I think the payload is maybe a bit hard to see, but basically here is like, this one is the address of the custom stack which is in the data section. So the benefit of this one is you know the exact value of you can fully control the stack. So in this one, let's say this one is the address which point to one of the ROP gadget where it's both EBP and read, which means load the value into EBP. So for this one, it will load this value into this value into the EBP. And the next one is both ECX, both EBX, or something like that. And you see this value is actually the exact VE minus printf. This one is the offset, which means the offset between exact VE and printf inside the libc itself. Because we know that the offset will be always constant, right? And at the end, actually, what we do is this one is the value. I mean, printf. Because you see in this one we have the gadget like something add EBP with some value, EBP plus some value. This one the address with the ECX value. So what we do is actually ECX we load with this value, and the EBP we load with this value. And this value actually the printf got address minus this one, because basically the gadget we have is at something like this, so we have to offset that. So basically, after this one, we actually get the God entry of printf. It actually will be added this value. So one is add this value, is become the address of the exact VE in the library. And the other way to do that is the God dereferencing. So in the God overwriting in the previous slide, actually we overwrite the entry of printf to the exact VE. So in case we don't want to do that, we can resolve dynamically and we just jump to that location. So the step could be like load the offset, which is, let's say the system and exact VE and printf, you load the offset of that one into the register. Add that register with the memory location of the printf God entry. Then once you have that value, you can just jump or call that register. For example, you need to have something like load register, add register, and jump. So this one, for example, this one is both EBX, EEX, and EBX. Then you can load that two value in. Then here you have some, like, let's say add EEX into that whatever the value inside this memory location to EEX. So now EEX contains the address of whatever libc function you want to resolve. Then the last thing you return into like clone EEX or jump EEX or something like that. For example, this one is an example of like you dereferencing from the printf to exact VE. So it's quite the same with previous example, except that at the end of the things, we actually call EX instead of call the printf God entry. So in this dereferencing, the printf God entry is still in stack. I mean, we don't modify that, we don't override the God entry of printf, but we just like resolve the address of the exact VE based on the current address of printf. So the question of all of this is, what is the availability of the God manipulation gadgets? So Actually, this is available in the auxiliary function, which is generated by GCC compiler. So which means any program you compile with GCC, this thing will be available. So we do have enough of gadget. It's just like this, it's enough of gadget for us to do the stage 0, the full stage 0 payload. And it's available in all of the binary compiled by GCC, which is pretty good. For example, got overwriting gadget we can find in the destructor or some detour ROS function and constructor. So this is actually contain enough of things for us to use for God overwriting and God differencing. So I mentioned before, like this one in this example actually available in something like this one or this one. So so actually for the catalog, right, we don't need to have all of the ROP gadget. We don't care about that. What we want to do is we want to have some way to be writing the exploit very practical, and it's reliable, and it will work in different across distribution and things like that. And it's not too much dependent on the binary itself. So that's why we were talking about those auxiliary function in the GCC, where it's actually is less dependent. I mean, I don't care about what the program doing this, because those gadget is always available in destructor and constructor function for of the libc of the GCC generated program. So actually we need only a few of gadget. Basically we need one of the load register gadgets, we need one of the add or sub memory, and this one is optional. I mean, it's not necessary to have it, but if there is available something like this, and we can do much more things. So basically we only need only a few of the ROP gadget, which is because you cannot really expect that you have a lot of different things where you can do like arbitrary computation in the real. So because the thing is very dependent on like specific target and things like that. So the way we're doing it, actually we're trying to minimize the number of ROP gadget just enough to do the state 0. Then based on the thing I just present, so we're trying to write some of the library where we can do all the automation of all kind of that thing we present before. So, you know, like calculate menu, calculate all that kind of thing, like God overwriting, like finding the ROP gadget and do the God overwriting, dereferencing, and all kind of that kind of thing actually will take a lot of time to do manually. So what we're trying to do is we're trying to have some of the tool where it can help to generate and search for the required gadget, help you to generate the state 1 payload, help you generate the state 0 payload, and load the exploit. So we call it a return-oriented exploit, make easy. So basically it's have the functionality to generate the gadget from the binary, from the library, libc, things like that, and help you to be some of the command line things to help you to do like search for specific gadget or something like that if you want, and it can have a generator to help you to automate all of the things you need. So something like this one. So this one actually we implement very simple ROP tool. So it's not because it's actually not required to have complexity here. And let's go for the demonstration. So we have the demonstration for the okay. Because my laptop has some problems, so I just borrowed the laptop from Mars. So I just play the video instead of having the live demo. So this one is an example of the vulnerable binary, where it's basically just noting the simple one with the string copy. This one is actually the system itself have like NX, ASLR, and things like that. However, the binary itself is so this one is demonstration of the ROP cell, which is the simple thing where you can do something like generate the gadget for the libc, for the binary, searching for different things. So we just, this one is just implement very basic, like try tree with like generate and help you to like searching for different things. We think that enough for building most of the things already, so we don't need to have something like very complicated. So here is an example of the exploit. So you see this one is an example of how you write the exploit for that one using our way. So actually we have the Python library to do that. So you can see you can just like specify like ROP payload something with the program, libc, and something like that. And then you can just set the custom stack. So this one actually it can be automated as well. But in case you want to specify by yourself, you can put it like this. That means this one actually the memory you find in the, let's say, data section or whatever variable memory section you want to use for the custom stack, like I mentioned before. Then in the library itself, it's already provided all kind of like God overwriting, like I mentioned before, or like trying to help you to build the state one payload, let's say set UID or clone some of whatever function, thing like that is already in the library, so you can just use it. So for example, for example, this one is like you override the get user ID, override it into the set UID things. So this one is unstable. That the library already provides you the way to do the God overwriting, so you don't need to know like how exactly you do the God overwriting and calculate and things like that. That one all automate, so you only need to call something like this, and it's all done by the library itself. Then for building the state one, for example, the state one, what I want to do is the first thing I want to do, like I call the set IEUID and make it into like 99 minus 1, 99 whatsoever. So I want to set it into nobody or whatsoever, something like that. Or maybe 0 if you want to become root or whatsoever, thing like that. Then for the state one, I can do the same thing for the state one. Like I do the God override, the set IEUID. Since before, right, I override the get UID to set IEUID. So now I want to do override again. So I override from set IEUID into this one, execve, because in the state one, I want to call execve some program. In this case, I want to call, let's say, cell, for example, /bin/cell. So what I can do, I can say, okay, I want to do God override. Then next, I want to do the state one execve, the target binary, and the /bin/cell. So this one basically is how you write the exploit with our library, with our tool. So it's very simple to do this kind of thing, and it's automate most of the thing which is complex. And after the end of this one, we can do the code to generate generate the state 0 and state 1, then just lost the program, and it's like automatically generate on the ROP payload to do multiple of the things like transfer the payload and set up the new stack, blah, 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 blah. So all of those will be done automatically, so you don't need to care about that. So that one is the exploit. So now you can just lose the exploit with the vulnerability program, and from here you can see, so this one is like I enable the debug thing, so you can see more information. So when you run this one and load the library, it will loading the gadget from whatever already generated, or if it's not available, then it will try to generating the gadget by itself. And then it will trying to build the state 1 and state 0 payload, and using the string copy function. And you see this one is generate a multiple of string copy things. So this string copy, multiple string copy, like I mentioned before, where the state 0 need to transfer the state 1 into the custom stack. So this one is the payload generated to do that. So basically the payload is like the address, and return address. So this one is like kind of like chain return to address kind of things, return to libc kind of thing, but this one actually return to the PLT entry. In case there's no string copy, we can override that one using the God overwriting or whatsoever to make it become string copy. So this one is the state 0 payload. So basically I need to transfer the multiple. So this value is this value is the value of the state 1 payload. So I need to transfer all of this value into the new stack. So basically, like I mentioned before, we are searching for B4 in the binary. So we know, okay, in this array, there's a B4. So we generate the string copy to copy that B4 into the new stack. Then we search for, okay, what the next value is 84, something like that. And we search for this string, and the longest as possible. So we find that there are 3 bytes inside the binary itself. We contain this, so we generate the string copy to copy like that. So one is done. This one is the state 0 payload. You see all the address and thing return blah blah here. Then this one is state 0. Then you see one is done. Actually successfully exploit. Then you have a cell here with the user ID in 99, where it's in the exploit before we mentioned. We actually want to set UID into 99. So there's another example is the libc problem in the CV 2010-2067. So here is a sample. So we just like using the RPM to install the libc tool, which is available in Fedora. So if you see in this one, we're trying to, the exploit actually we have the tool using the library to generate the TIFF file. When you open the TIFF file with that file, actually it's exploit the bug, and actually you see it's run the BC here. This one is the BC command, BC program. So we just try to do something like that. So for example, this one is some of the library itself. It have the PLT, got entry, rewrite, thing like that. So you can look in the thing like got overwriting, that kind of things, where it's do all the thing automatically for you. So you don't need to care about like how exactly you can do that. Got dereferencing, And for the libtip, the exploit we just showed for the libtip, right? It's also the exploit for this one is pretty simple and short. The same thing, I do the got overwriting execve with the get option something. Then you see previously it's called like BC. After I in the demonstration actually run the calculator command program. When I open the tip file generated by this tool with the lib tool. So you see it's simple like state one with execve this program. Then I can do like overwriting with turn string k compared to string copy. This one example of this. And you see the exploit is basically just a few lines like this one, and it's generate all of the chain return to libc and ROP get to do all kind of things. So I think I'm out of time already, so it's almost done as well. The countermeasure, so our methodology actually doesn't work with the PIE. However, if you, in some cases, actually you can trying to prove out the base as read. For example, is the server side, where it's keep fork or the new connection, which means every time it fork, it's still the same memory map. So you can do that, and you can prove out the base as read. And once you have the base as read, you can apply the same techniques to do that. And the PAE is not widely adopted by vendor anyway, so they only use it for some critical network application. We also support for the macOS, but however macOS is much simpler because the dynamic loader here is always load at the fixed location, and the import is reliable. So basically, it's very simple to do this. You still can apply the same methodology where state 0 is to do the sequence of the data from the dynamic loader itself, and the second, and you can do the more simpler version is like some small cell code loader, and the state 0 is the cell code. So this one is for example of this very simple thing for the macOS, and it will work. But however, this one is just some extra thing. So I think I almost finished with the talk. So any question?
If you do have a question, please raise your hand.
I was just asking, have you released the ROPEME tool? Is it open source?
I think the first version already released on the website, but the new version we haven't released yet. So the new version support a lot of different OS and things like that.
Okay, if there's not any more questions, I would say we're actually already going into the coffee break.